Um, Hi, good evening. Today I'm going to talk about the hybrid quantum classical systems for NISQ devices with faster gates on EEG binary classification with base optimization. This is the one conference article I am glad to publish here on behalf of the East China University of Science and Technology. Thanks to the supervisors I've been cooperated with, who's the Xiaochuan Pan and Wang Yubing professors. And so basically here are the contents we covered in this article. The quantum computing is our main theme, and we include the noise, include quantum computer. So, which means there are errors, and the fast gates operated are mainly Pauli operators. And the EEG are the data set which can be downloaded from open source website. And here is a 29 channel data. And the hybrid quantum classical system is our main algorithms, which has two parts, where the first is the base optimization, which are the classical part, and the second part is the VQE quantum computation part. The results are mainly also conclude two parts separately, and there are the matrix like confusion matrix, fidelity as the evaluation of our variational quantum estimation. The discussion parts are generally a summary of the conclusion and some further extension or future directions. So, if talk about quantum computation, we usually think about its advantage of the possibility to store more states than either 0 or 1 in a single qubit. And it usually utilize the quantum phenomena like here mentioned, and those three are the basic phenomena we are usually familiar with. The superposition on the additional of peaks, like and the negative peaks. The entanglement of the multi-bits, which gives no independent state of any of them. And the interference here, the most famous one is the Young's interference experiment with the quantum with the wave-behaved particles. The NISQ here mainly focus on the compose with quantum error correction. So it's not feasible and ineradicable hardware errors with modules. That's why we needed to compute with the fast gates. and of proper size. Here, the polygates we mentioned about are usually the H, X, Y, and Z, those can also be generalized with the U gates, with phi, theta, and another constants. The definition of the quantum computer here generally proposes the error correction and the fast gates with operations on multi qubits. For our paper, we compare the efficiency with the 5-qubit small circuit and the aggregated and the 15-qubit large circuit. So, and because it's a diagraph here, it's determined, for example, the phase in each epoch actually determined by the variational quantum estimation method. In this paper, we specifically include a special form of the wave function. It's a sinusoidal wave function. Here you can see I choose the retro solution here. So it's theta is iterated every time in each iteration, and it's based on the expectation of the wave function, which is basically a sine theta plus phi, a sine theta plus b plus phi. And actually, usually, defaultly, our theta is set fixed as pi over 2. So here, then let's back to the EEG. EEG is also downloaded from the open data. And in this paper, it's the 896 samples on time domain and 29 channels, as here you can see. And the label, which are binary, are recorded, annotated manually by 2 physicians separately, and finally classified into 8 features. The sample frequency is 20 kHz, and the duration is 0.0448 seconds. So we first used the Hilbert transform and the ERP extraction to make it stationary and decoherence. So here are the before pre-process and after process, pre-process here. And we have also observed the STIM, which is the stimulation of each second on different band. In all, we have mainly 8 bands here. It's also included in the article as the delta, theta, alpha, mu, SMR, beta, and gamma, those intervals. And it's here are on the time domain. And it's actually recorded, analyzed on the whole domain, although here it's 0 to 200, but we divided them into 5 in all, as we have 896 samples in each trial. Here we just have some examples shown here. Like you can see, they're mainly they are distributed mainly in some similar pattern, which can actually also be. This is actually from the four of our interests. There are 4 channel we choose, and so here we can see it's in accordance with the theory that EEG are not spatially correlated, mainly, as here on the 4 different channels, they have something similar, almost the same behaviors. And the same thing is with the asymmetry of the beta and the alpha band, the property as well. So as our formula writes here about the symmetry, it's about both beta and alpha asymmetry, and which is composed by frontal and the temporal area. And actually, it don't have to be only in alpha and the band and the beta band, but we choose these 2 to observe, to analyze, because mainly the information are more are of higher frequency here in our data. And later we also apply the t-test and ANOVA test to the asymmetry. So with the stars parts are the band where they are significantly different. So it shows the beta temporal area is significantly correlated with the alpha different from the alpha frontal, and the beta temporal are significantly different from the beta temporal beta frontal temporal. And then this is the part I have introduced, the exact formula of our wave function expectation. through optimize this part,